That's like a serious intro. It makes me look like a serious person. So welcome everyone to NDC London 2026. It must be weird hearing that welcome to London from an Australian voice, because I know you don't have many Aussies over here. Thank you. I was hoping there was a joke there. Yeah, the first 10 people I spoke to were Australian. So as you saw, I have been a developer for a while. I've been around NDC events, but I haven't actually been to NDC London since about 2017. So it's really nice to be back. I've been a developer for about 25 years in a paid way. I've been writing code for 30-something more years than that. But lately I've been in developer relations, so DevRel, so talks and things like that. And as a result, I've saved companies billions and billions of dollars just by not being the person writing production code anymore. So I've done the coding, I've done the other stuff, and I only found this out the other day, actually. I visited my boss in Northern Ireland, and I only found out the other day that I was inside the top 10 people in the world, or the first 10 people in the world, to actually use GitHub Copilot, which was kind of one of the first AI coding tools out there, which surprised me, actually. I knew it was early, but I didn't realize it was that early. So I've done the coding, and I've done the AI stuff, so I've been around for a little while. And as a result, I've written a lot of code I'm really proud of. I've written a lot of code that I'm not as proud of. And so I want to start with a little bit of a quiz for everybody here. I want to know, has anybody ever committed or deployed something to production that they didn't quite understand? The code, they didn't quite understand exactly what it did. Okay, we've got 5% of the audience put their hands up, which means we've got about 95% liars in the audience, which is it's a good start. So I want to tell you a story about one of the bits of code that I'm actually the most proud of, ironically, which I didn't quite understand. This was back in the day, I'm not going to date myself, but back in the day, early days of .NET, where we didn't really have all of the libraries to do everything. So I worked for a company in Australia where we had a head office and we had a bunch of franchisees all over the country. And this was a little while ago in Australia, so uploading files and things was something we needed to do, but we had this teeny tiny little internet pipe in Australia. Now it's slightly bigger. And so we needed to make sure that the files were really small. Now we didn't have a compression library inside .NET at the time, so I had to write my own. And so I did what any good developer would do at the time. I opened Wikipedia and I looked at an encoding algorithm. Called Huffman coding, or Huffman compression. And before you ask, yes, Wikipedia did exist, so I'm not lying. It had been created the year before. That's true, actually. So I read it all, and I worked out how Huffman coding worked, and I wrote some code, and after a few attempts, I had a compression algorithm and a decompression algorithm. And I tested it with a bit of data. Put some in, decompressed it, pulled it out, and it was smaller, which is great. It all worked. So ship it to production, right? Everything went great until people started using it with real files. Now, it turns out I'd copied the algorithm. Like I kind of took what was there in Wikipedia and I turned it into code. But I didn't really understand what I was doing. I'd just kind of taken some pseudocode and turned it into real code. So to get it fixed, while everybody was complaining that the thing didn't work anymore, I kind of had to work out exactly what was happening in this algorithm. So yeah, it didn't go so well to start off with. Now, to explain what went wrong, I'm going to take you down a rabbit hole, and we're going to explain how Huffman coding actually works, or Huffman compression actually works. Now, is this going to be something that's useful for your jobs moving forward? No. Is it going to be useful, though, for explaining other things in your jobs that you might encounter in the future? Also, no. All right, let's start. So to do this, we're going to take a really small phrase, and we're going to compress it. I'm going to show you how to do the compression. So the really small phrase is, sorry, what now? With a question mark at the end, right? So there's some repeated letters. We can see it'll be compressed. OK. If we convert this to UTF-8, we can use full byte, 8 bits, and so we get this, sorry, what now? This is just ASCII, UTF-8 encoding. So we're using 120 bits now to encode that. So that means we need to send 120 bits across the wire, which at the time in Australia was a big deal. Now, you might notice as well, sorry what now has 15 letters in it, or 15 characters, including the spaces and the question mark, but there's only 10 unique ones. So immediately, if we only have 10 different options, immediately we only need 4 bits, so we can halve this straight away, right? And so now we're at 60 bits, which is good. So if we just sent those 60 bits, we still could get the message across. But that's only 10 characters, and if you know your binary, you know you don't need all 10. So we can do a little bit better than that. We could use 3 bits for some of them, and 4 bits for some others. If you really wanted to, you could use 2 bits for some of them, I guess. But the difficulty is you can't have one of the encodings, one of those bits being a prefix of something else. So you can't have 110 and also 1100, because then when you're reading it back, you don't know when to stop. You don't know which one of those it is. So you need this prefix coding, is what they're called. And a great way to do that, to fast forward a little bit, is to build this binary tree and then put the letters at the leaf nodes. And the more frequent the letter is, the higher up it can go, because then you only need 3 bits. So the very far left node would be 000, and then next would be 001, and then 0101. Anyway, you get the idea. So we put the letters in, Y is repeated, space is repeated, O, R, W are repeated, so they only need 3 bits, whereas the ones that only appear once need 4 bits. So you can kind of see where we're going with this. Now we have this column, and we've saved 9 bits. Yeah, thanks. There was a woo from the front. And again, in Australia at the time, 9 bits was 10, 15 minutes. So, so we've done really well, right? So there is a problem though, and I don't know if anybody's noticed the problem yet. When we store information or we transmit information, we use whole bytes, right? So we use like multiples of 8, essentially, bits. So when we're doing UTF-8 encoding, that's fine. Each letter is just a whole byte. But when we're using our little Huffman encoded ones, we end up with 3 bits at the end. You can't really just send 3 bits. You've got to make a whole byte. So you'd have to pad it with zeros, probably. The problem is 000 is a letter. So what was happening was when we decoded it, instead of saying sorry what now, we get sorry what now Y explosion, because 2 zeros is not a thing. That's best case, by the way. Worst case is it just keeps reading into memory, which can be fun. So it didn't work. Now, the solution to this is pretty simple. You just count how many characters there are and send that information along with the thing as well. So once I'd worked out how it got put together and how it actually worked, it was relatively easy to fix. But I didn't understand it to start off with, so I didn't really know why it was broken. So we've got a solution, right? What I want to ask you, though, is what would happen now, like today, with modern development? This was not pre-internet, Wikipedia worked, but this was like pre a lot of coding tools, definitely pre-generative AI, right? So if you had that same problem now, you needed to compress some bytes to send over the wire and then decompress them afterwards, what would you do now? You'd probably just do something like this. You know, this is VS Code, GitHub Copilot, but you know, there's any number of these tools. Write a function to compress some bytes. And then some magic happens, and then you get this. Now, does that work? I don't know. Probably. Maybe. It's a really good question, right? The LLM that's doing this work is kind of a black box to us. And while you're listening to me now as well, I just want to point out that there are a ton of extra talks later in the conference that are really useful for digging a bit deeper into some of the things I'm mentioning. So if you do actually want to know a little bit more about what LLMs do, Michelle Frost has a really good talk later on, is it today? No, Thursday, about interpreting LLMs and reading between the lines. So if you want to see a little bit more about what's actually happening, that's a really good one to go to. So yeah, we don't understand what that code does, and I could read through it and try and interpret it, but something like that is going to be at the limit of my abilities, frankly. Which is good that we have libraries, and a little bit more on that in a sec. All right, just by the way, a little addendum to this story. It turns out that that solution didn't really work either. Does anybody know what this is? Probably not. It's a scanner. A scanner is like a dumb camera. You put some paper in there, and it's like a photocopier, but you don't get the paper out, you get the image on the thing. Anyway, doesn't matter. So what happened is one of the franchisees decided to scan a document at the highest resolution they possibly could and then save it as a TIFF format. Does anyone know what a TIFF? Don't worry. And TIFF can have some compression in it already. And so you got this massive file that we had to upload, and I was like, oh, that's fine, we can compress it using our thing. But because it's already compressed, there's not a lot of duplicate bits or patterns and things, so it didn't compress at all, and the whole thing exploded, so it didn't work anyway. Yay, technology. So just so you know, it didn't work. My point is, though, I wasn't able to fix that problem until I understood it. So the lesson here is if you don't know how it works, then you don't know it works to some extent, right? It might look like it works every time, but if I don't know how to explain what's going on, then I don't know that it's going to work every time. Now, I know everybody here, you're at a conference about software development, you care about the stuff you're doing, you care enough to know what the code you have does, but you can't make everybody else care, right? So there are some things we'll talk about a little bit later on to help with that, but I want to challenge you a little bit on the idea of, yes, you know what your code does. There's a lot of .NET devs here. I'm not going to ask for a show of hands, but I know we're a little bit .NET heavy at NDC events. Does anybody know what this code does? And I'm going to give you a minute because it's not super straightforward. But just yell it out if you know what gets written to the console. I'm going to drink. Anyone? Nothing? It's not nothing. 0. Wow, everybody got it at the same time. It's very consistent processing. Yeah, 0. Yeah, good job. 0 is the right answer. Except if you happen to compile this in September 2015 using the latest version of the 64-bit compiler for .NET 4.6 in release mode with compiler optimization turned on. That's pretty specific, right? But that's what happened. So it turns out that around that time, Microsoft released a new version of the 64-bit just-in-time compiler that had some unexpected behavior, including, and this is a little bit hard to parse, but generally, including that an if statement inside a catch or a finally might get optimized out even when it shouldn't. This is a real thing that happened, and in their defense, they fixed this later on. But what that means is, at that date, on that time, this could have given you 9 instead, but only in production. So, do you know how your code works? Probably. But it's a little bit dangerous sometimes to just assume probably. Now, this is a massive outlier, right? This doesn't happen a lot. But I just wanted to make the point that there's stuff underneath your code that you maybe don't understand so much. All right, so .NET developers, anyone know what this does? Sorry, I'll scroll a bit. You didn't get the whole context then. This is also .NET. This is MSIL, so this is the intermediate language. So your .NET gets compiled into, to simplify, into this, and this is what's in the DLL, and then depending on the system it's running on, then it gets interpreted to machine language and so on. But this is the same code, it does the same thing. But you can't look at this and say, oh, I understand what that does either. And this is not even its final form, right? There's kind of another layer on that as well. So yeah, do you know what your code does? Probably. But you're relying on a lot of stuff, right? All right, if you do want to know, by the way, if you do want to know a little bit more about what your code actually looks like and how it translates, because most of us are kind of up at this level, and we know intellectually there's stuff that happens underneath the layers below us, but we don't really care about that a great deal most of the time. I can't recommend this book enough if you do want to know about that stuff. This is a book called Could Code by Charles Petzold, and I think this was scanned using that same scanner I showed before. I only just noticed that. This is really good. It's a book with a lot of chapters, and it starts right from like how do you encode information and goes all the way through bridging hardware all the way up to software and programming languages. So you can kind of understand from the ground up exactly what your code is doing. Just to put it in perspective as well, you get to logic, like logic gates, on chapter 6. So it tells you everything, right? So there's a ton of stuff that happens underneath what we write in code, and we rely on that, right? Anyone know what this is? Has anyone seen it before? Yeah, one person, that's good. It is a toaster, good job. But this was part of a project by a guy called Thomas Thwaites. And basically, the project was, as part of his Masters of Arts, was he wanted to build a toaster from scratch. No bought components. The wires and things, he had to mine and refine the metals himself. He had to process and create the plastics, all that kind of stuff, right? It took him 9 months, and it cost about 250 times what it would cost to buy a toaster just down the road. And incidentally, if you want to see this toaster is on display at the V&A Museum just down the road. I wanted to get there, but I had a thing that I needed to write first, so I didn't quite make it. But I am going to try and get there later this week. But that toaster is there, right? The point of this project that he did was really just to demonstrate that there is so much that we are building every single thing we create on, right? Creating a toaster from scratch is not feasible. We are building everything we do on a framework of a ton of work that other people have put together and other people have done. And it means that, to some extent, there's almost no entirely knowable systems left, right? When you build something, you're relying on so much other stuff, right? And that goes double for, software development, right? When you write some code, there is so much work that other people have done ahead of time. So I want to do another example, right? This is a Node Hello World web application, right? So all it does, you hit port 3000 on your local machine, and it will reply with Hello World, just as text, right? This is using Express.js, which is an NPM package. It's a really simple, basic web server, right? So this is the entirety of the code that I wrote, and I handwrote this like a pleb, right? But this is dependent on this one library, Express.js, right? And it's just one library, one dependency. There's a really good argument you can send to npm, the npm command line, ls, which tells you what your dependencies are, basically. And if you do the -- all, it gives you your dependency tree. So what does Express rely on? What is the dependency there? Not much. So if you do it without all, you get 1. If you do it with all, you get this. This is 123 dependencies. And yes, a lot of them are duplicates. You can see over there, there's like deduped. So it's actually only 65 dependencies to make that tiny bit of code run. All right. Now, this is potentially thousands and thousands of lines of code that you didn't write, written by thousands and thousands of other people who you are depending on to get that code exactly right. So you have this huge dependency on a whole lot of stuff that you didn't write. And incidentally, this is where enterprises, they've kind of come around a bit, but for a while, enterprises were terrified of this. This is not our code. We didn't write this. How do we know what it does? I think they've started to realize now, mostly, that this is happening anyway, right? There is nothing you can use for any operating system that doesn't rely on a ton of open source anyway, so don't worry about it so much, to be a bit flippant. But also, by the way, for those Node aficionados, you don't need to use Express.js to do Hello World. You could just do it using the HTTP thing that's part of Node. So no dependencies, right? Except for Node, which is open source. Anyone know how many lines of code Node is, roughly? About 10 million. So still a little bit of a dependency on some other people's code. All right, so where does that leave us, right? I just started earlier on by saying if you don't know how it works, then you don't know how it works. And then I just spent a little while explaining to you that you actually don't know how it works. Therefore, we don't know how any of our code works. So that's pretty a great start to a conference about programming, right? None of the work you do can be interpreted, right? It's great. Where does that bring us in this kind of age of AI? Should we just, give up? We haven't We don't know how any of the code works, so we just write some stuff and YOLO it into production. Ultimately, it comes down to the fact that building software is, to a large extent, an exercise in trust. We are trusting that when we write the code, and we can reason through that code, that it is going to run as expected. The dependencies we're relying on are going to do what we expect them to do. The platforms, the frameworks, the operating system, the hardware is all going to do the thing that we expect it to do. You are trusting that that code you write is going to create the right little bits of electricity going into the right little bits of special rock somewhere in West US, right? And we have to trust that. And more than that, actually, I would say in most cases, it's better to trust that code than to trust your own code natively. So has anybody, by the way, had a coding test in a job interview where they've been asked to sort a list? Anyone done that? Yeah, cool. You know what the correct answer to that question is? That, right? Anything else is pointless, right? I guarantee you the people who wrote the language and wrote the sort algorithm and the people who wrote the compiler, they are better at optimizing a sort than you are, right? And if you can't rely on that, if you can't rely on the fact that a list.sort in a language that you know is going to do exactly what it's supposed to do, wow. I mean, yes, you have a problem, but the bank down the road that has all of your money, they're probably having a really bad day, right? Your little inventory management system that doesn't show the items in the right order anymore, that's the least of your concerns right now. So maybe you should just calm the fuck down. Like, you've got to rely on this stuff. You really do have to trust that it's there. However, this is the code that you didn't write. This is the code that other people wrote that you were relying on. And open source kind of helps with this as well. There's millions and millions of people relying on this code. Most of them are more determined to make sure that this code works than you, or at least in my case. And so there's somebody else who is going to look at this code and make sure that it works. And there are processes in place to make sure that we don't pull down all the banks for the most part if something goes wrong. Right? Incidentally, there is another talk later on today or tomorrow, I think, on the CrowdStrike incident too. So if you want to know when that doesn't happen, it could be a really good breakdown of that. What we want to do though is we want to trust our own code. Right? The code that we write, we want to trust that it's going to do what we expect it to do. And this is where this new world of generative AI can potentially cause some issues, right? So I asked some questions before. Does anybody know what this code does? We showed you some .NET and then there's some IL. Does anyone know what this does? Do you know what the output of this will be? No. You don't even know the shape of the code that's going to come out of this one. You could guess, sure. And admittedly, when this does give you a response, right now, the current state of AI, generative AI software development, it will give you code that you can look at and work out, how does this work? But if we stop here and then just YOLO whatever comes out into production, then we're stepping up that level of I don't know how this works. And so this is what some people do. And as somebody who has worked in finance and has had exposure to medical systems as well, the idea of just taking the output of something like this and putting it into production is terrifying to me. On the flip side, I've also been in DevRel for a while. This is a screenshot from the last GitHub universe, and in the background behind Jessica Dean, you can see there is an app that lets you download a wallpaper that has information about your own GitHub profile. That application is almost entirely vibe coded because who cares, right? If that breaks, not a big deal. And in fact, in a lot of cases, if that breaks, then we just don't click on those parts of the app on the stage, right? In that case, I can totally understand vibe coding something and throwing it in prod. Right? So there's this middle ground, right? There's this position where we need to be, appropriate about what the AI gives us. And we'll talk about that in a sec. I want to introduce you to this guy, though. This is Buck Schlegeris. Hopefully I've pronounced his name correctly. He's actually Australian. He's from Townsville. But he runs a company called Redwood. And they do a lot of AI security stuff. So looking at malicious, or not malicious, but misaligned AI systems. So is it actually doing what you want it to do? And he tells a story in a YouTube video for Computer File, which is a great channel, about he really early in the days of GPT-4, he thinks, he wrote this agent, and it was like an agent loop. By the way, I'm not going to talk about Ralph in this talk. An agent loop, there's an audible talk to me later. An agent loop, basically, so an AI agent that just did some work, and it would try to solve a problem, and if it got a bash command, it would ask him if he wanted it to execute that bash command. But that took too long, so he just executed it anyway and did this in a loop. Now, he had a scenario where he had a machine somewhere on his local network, and he wanted to find that machine. He didn't actually physically know where it was, but he wanted to know where it was. And so he asked his little AI agent to go and find that machine. And so, of course, it did. He went and did something else and came back again, and he looked through the logs, and yes, it had found the machine and then bricked the machine, despite him saying, when you found it, stop. What had happened, he's kind of pieced this back together. What had happened, he thinks, is that so when you log into a Linux system and there's an update to Linux available, it can tell you, hey, do you want to run an update? Here's how you do it. It saw that bash command to update the operating system, and it thought, cool, I'll just run that. And so it ran an update to Linux. And then it got a bit confused about why things were taking so long, and so it kind of interrupted and left it in this unrecoverable state. And so that is an example of giving an agent a little bit too much control. By the way, if you're interested in this, I think both Heather Downing and Ben DeCry later in the conference both have talks about permissions for AI systems, for LLMs, and giving them the permission to do the things they want as well. So if you want to drill into that a little bit further, also worth doing. So the lesson here, right, is that there is probably a happy medium, like a point at which you're okay with letting the AI do what it wants, right? But how do you work that out? How do you work out what you're happy with? So I want to introduce you to something which is not new at all, but it's a really simple graph. There's a very clear relationship when we do generative AI for software development between the scope of the change, like how much you've asked it to do, and the quality or the accuracy of the code you get out. If you ask it to do more stuff, it's more likely to make a mistake or make a mistake. It's more likely to not really understand exactly what you want. Right? And there are ways around this a little bit, but the graph generally looks like this. And so if you go from a line of code through to a full application, when it's a single line of code, not only does the quality go up because the scope of change is really narrow, you can really define what's there, but your control over that quality and accuracy can improve as well. If you're just asking for a line of code in a function, and you've already got a test around that function, that's going to be fine. You've got some guardrails around it. You can test whether it works. If it's an entire function, techniques like TDD, like test-driven development, you can write the test first and then ask the AI for the implementation. And then that's likely to give you a pretty high quality. In fact, you can go on from there and do things like, hey, given this function that you've given me, can you write some additional tests for any edge cases that I might have missed, and get those. Even ask it to explain what it's done. Are there any improvements that you could make to this code, and iterate a little bit that way. But in general, you have a lot of control over the quality and the accuracy of what comes out. But an entire application is a different story, right? You can't use techniques like TDD effectively for an entire application because you don't even know what the shape of that application is. It could give you, HTML in a resulting web page that looks identical and have 6 different implementations to it. Right? And the more information you get it, of course, the more precise it's going to be with the implementation. But it's very hard to test that kind of thing. And again, Debbie O'Brien has a talk later on, when is it? Today, later on today, about testing techniques as well for AI-generated code. About that. So if you do want to know how to do this a bit more effectively, that's also worth going to. I did tell you there's a lot of other talks that drill into this stuff. So what you do basically is, based on your scenario, and it does depend on the scenario, you can kind of pick what level of accuracy or quality you want to accept. And this doesn't mean just YOLO into production. It means, I'm pretty confident that this works. Let's run a couple of little tests. Okay, it's fine. So you draw this line of like what is acceptable, and then come down to this scope of change. And anything beyond that scope of change, sorry, that way, anything beyond that scope of change, maybe you don't trust the tool so much. It doesn't mean don't ever do it. It just means a lot more rigor around, what you're looking at. Now, the scenario changes a lot as well, because really all you're doing here is doing a risk assessment. Like you're looking at the risk and the impact of failure. What happens if that code goes wrong and then gets all the way through to production? How bad is it? Now, I've been in DevRel for a while, and like right from the really early days of Copilot, there was a tool that I asked it, an application I asked it to make, and it's been pretty good all the way from the start, but it's incredibly accurate now if you ask for this application. And it's one if I'm traveling with a bunch of friends and we're all paying for different things, keep track of who has spent what on what, for who, and then at the end of the trip, who owes who money. So, day one, maybe I buy dinner for everybody in the group. Day two, maybe I go to a show with just 2 people and, John pays for it, and so on. And so all the way through the trip, it's just balancing this money, and at the end, who owes who money. Now that's relatively safe, so my risk appetite for that is quite high. If it gets it really, really wrong, somebody's going to notice, right? And if it doesn't get it wrong by a lot, it's a little bit of money between friends. It's not a big deal, right? And it's done a really good job. So my risk appetite for something like that is quite high. But if you compare that to something like write an application that will automatically move money between my company's bank accounts so that we can make payroll just before that's due, that's something I probably don't want to trust entirely. And those are entire applications or entire big pieces of functionality, but it doesn't have to be that big either. Can you imagine asking it to write a function to tell you what the appropriate fentanyl dose for Mr. Smith is for this date, given these values? I don't want that to go wrong, right? So my risk appetite there is really, really low. I'm going to test the crap out of that code. So it really depends. For that example of the money changing hands, maybe it's here. So I'm okay with it being incorrect. But then the fentanyl dose, is way up here, and I'm going to be, really strict about that. So this probably isn't blowing any minds, right? I'm just put it in a graph. Everybody knows this. It's case by case, right? What is more interesting, though, is, and potentially more problematic, is the fact that these AI generative tools are getting better. It's really hard to argue that compared to when they first came out, given an appropriate prompt, some more information, the right amount of information in the right context, we are going to get better and better code as these models improve. It's very hard to argue with that. I'm a little bit on the inside GitHub, and so I've seen we keep accuracy metrics on these things, and so we are getting better. So what happens when these tools keep getting better? Well, what we're really doing is we're just raising that line a bit. So the quality is going up across the board. But then if you still have that same level of quality and accuracy that you're okay with, it changes like this. And if you don't reevaluate based on the impact of something going wrong, then more and more stuff can go wrong. Or not more and more stuff can go wrong, but you're asking for more and more from the AI, but the impact is still horrific. So before, that might have been my risk appetite for the transferring money between bank accounts thing. But now, according to that same graph, I'm okay with the entire application being written by AI. Right? And I know what you're saying. Obviously, as it's getting better, you're not going to just change how much you're okay with. The problem is we're not always conscious of this. Right? We're really good as humans at pattern matching, and we tend to think, if something happens, if something works 95% of the time, it works every time. Right? You see that with dialog boxes that pop up. You just click OK. You're like, I don't know what that said, but every time they come up, I click OK, and it's always fine. Right? So the same kind of thing. If you use an AI system and it gives you a response, and 80% of the time, 75% of the time it's right, then you're still going to check it, right? You're still going to make sure that it's okay. But if it gets it 90%, 95%, 99% of the time, if it gets it right that often, you stop paying attention. And that's just the way we work. And that's going to be a problem all the way up until the AI is able to get it right 100% of the time. And friends, that is not going to happen. We can't even describe what we want anywhere near 100% of the time. So there is not going to be a time where that graph goes to 100%, it's a flat line, a flat red line, okay? So we need to be conscious of this. We're also not very good at judging this stuff either. This is Geoffrey Hinton, I think sometimes called the father of AI. He famously said at one point that it was immediately obvious, or incredibly obvious to him, that we should stop training radiologists, so that people who look at MRIs and X-rays and so on to look for disease and problems. He said we should stop training radiologists because it's incredibly obvious that within 5 years, computers will be better at that than humans. He said that in 2016, so more than 5 years ago, and we are still definitely training radiologists. Now, in his defense, last year he did say that he got that one wrong. He admitted that. But really all he did was he got our risk appetite wrong. Like, he didn't judge that correctly. Because really, there are a lot of AI systems that work in radiology, and what's happened, rather than just replacing people, is they work hand in hand with people. Especially in the US, where there is a bit of a shortage of those specialties. In the US, they tend to use AI as a first pass to identify the things that the radiologist should look at first. But there is no case where the AI system just looks at the scan and says, this is fine, let that person go home, right? So not that great. This is the father of AI, got it wrong, right? Again, there is another talk, if you're interested in that side of it as well, on Thursday, I think. Agata, I don't know how to pronounce your last name, I'm sorry. Chudinska, I think, actually has a talk on AI systems in MRIs. So that'll be fascinating if you are interested in that stuff as well. So even though we're not great at our risk appetite, the systems are getting better and so on, that's arguable that the systems are getting better. Some people don't feel like that's the case. I would personally disagree, but they think they are getting better. I think one thing we can all agree on though is that they're getting their meaning. It means that we can write code faster. Now, I want to be really clear for the people in the audience who are skeptical of this stuff. I want to be really clear about what I'm saying here. We can write code faster. It doesn't necessarily mean that the code is better, right? That depends a lot on how you're doing it, what you're trusting it with, and things like that. In a lot of cases, we don't have to write the code. Like fingers on keys keyboard, we're not really writing as much code anymore, so it is faster. And we can kind of get away with a hastily written prompt in some cases as well. Here's some stats, by the way, from the last GitHub Octaverse, which kind of looks at repos across GitHub. The numbers are a bit, don't make a huge amount of sense. The most important thing is that there is more code. There's 26% more code than there was last year, but 23% more PR merges, so that code is actually getting merged in as well. But interestingly, and it's not in any of the stats that we've released, but the mean time to merge is going down. So interestingly, there's more PRs, yes, but they're getting merged faster, which is interesting. And even if you're still skeptical and saying, well, that just means we're getting more terrible code in our production systems, the actual merged code in PRs is about 80% more likely to pass builds than it used to be as well. So it is better code by our own builds and CI and CD systems as well. So based on the stats, the code is not worse. We are moving faster, but the code is better. And that is largely because we have these systems around already for existing code bases that give that rigor to the code that we're writing, whether it's us or whether it's the AI. Right? I firmly believe that we have a lot more control over the quality of AI-generated code than most people think. We hear a lot at GitHub as well, like, oh, hey, I opened a new file and I wrote a prompt and it gave me rubbish. Like, well, that's not the way to use it. There are a lot of talks later on as well about how to more effectively write code as well, but the quality of the code doesn't need to be worse. And even if it is, you care, as I mentioned, you care about the code you write, but you can't make everybody else care. So for the people who don't care about the code in your team, you still have all of those same solutions that you did before, for the most part. So we're talking about applying the same level of rigor to the code and the same gates and the same guardrails as we always did, right? Even though the problems are a little bit new just because of the pace, the solutions aren't, right? We've still got things like testing and code reviews with other people and CI/CD and all of these things that we always had. And these can still prevent bad code, whether it's written by a person or written by an AI, from getting into production. But they have to work. If they're not effective, if they weren't effective before, they're not going to be effective now. And worse, they're going to be ineffective faster now. So you'll get worse code or you'll get bad code into your production systems really badly, like really fast, sorry. Bad code faster, that's what AI promises. Don't quote me on that, sorry. One story about this that I want to tell you as well is a company in Australia, and it was a pizza company. I am changing some of the details and leaving some of them out just to protect the innocent, by which I mean me, because I don't want to get sued. But there was a software company that wrote some code for for pizza delivery or a pizza system in Australia. Sorry. Now we have this thing in Australia, or at least we used to, I think, called Tight Ass Tuesday. Right? That was his unofficial name. Basically, it meant that some things like pizza and movies and things were a little bit cheaper on Tuesday, probably because people just didn't do those things on Tuesday. They'd just gone back to work. So what had happened is on Tuesday, this pizza chain had decided all of the prices were a bit cheaper. All right, so what that manifested as in their code base was that all of the tests that they had around, do we add up the prices correctly? Do we apply vouchers correctly? Things like that. They all worked perfectly. All the tests had to pass every time, except on Tuesday, because the prices were different on Tuesday. So there was a suite of tests that failed, but only on Tuesday. Now, what happens if there's a critical bug you need to fix on Tuesday? Well, you got two options. And the first one is what they tended to choose, which was, these tests always fail on Tuesday, so let's just not worry about them, right? The tests all fail, but it's Tuesday, so don't worry. So because of this, quite often, well, no, not quite often, I don't know that for sure. You either deployed code that was potentially broken because you didn't have that robust, pipeline in there. You deployed it on Tuesday and then crossed your fingers because all the tests failed anyway. Or you just didn't deploy on Tuesday, which was also an option and just as unacceptable, right? So all of this is the DevOps lifecycle thing, blurred here because we don't need that this early in the morning. Also, I don't know where this image came from. The whole DevOps lifecycle that we used to have before with automated testing and continuous integration and your testing environments and QA and deployment automatically and all that kind of stuff, that all still applies here and should still apply. And that's easy to do with existing systems and building up new software based on generative AI there, but it's actually kind of hard to do if you're doing greenfield stuff. You need to think about this. But if you wrote an entire application with a prompt in a CLI or something, and then YOLO'd that to production, you're not going to have these systems in place. You're not going to have the tests. So you really need to look at that risk profile that we had before and decide how okay you are with that untested, ungated code getting to production. If we still want some quality in the code that we're producing and putting out there, then we need to think about that and work on those things a little bit better, a little bit more, rigorously. Now, the good news is there are efforts now to do that. So at the start of the AI, generative AI, hey, it can write all your code for you. At the start of that, the key was, dump out as much code that's working as possible. Like that was the best thing. That was the ideal for all of these AI generative tools. Now what we're finding is that these tools are being applied to different parts of the lifecycle, the stuff that's around writing the code. So writing the code itself, easy. But the techniques around writing good code are becoming more and more important. So one example, for example, is Spec Kit. So this is an open source toolkit. It basically means that rather than just dumping code out based on a prompt, you are working through that same lifecycle that you would normally do as a developer, where you define a specification of this is the application, this is exactly what I want it to do, this whole big requirements document. And then you go from there to a specification, and then from there to breaking it down into tasks, and then there to implementing those tasks individually. So the same way you would break an application down when you're developing it in a team. The key thing here is that you still have control over all of the outputs of those stages. You're not just throwing it there and letting it go. You are looking at the requirements document and modifying that and making sure that that's exactly correct. Looking at the spec that's getting created, making sure you're modifying that so it actually reflects what you want. And then the tasks. Which tasks are wrong? Which ones are okay? Which ones need tweaking? And so you're in control the whole way. Now, it does move you as a developer a little bit away from actually writing the code and a bit more to guiding the AI systems to doing the work. But it results in much more trustworthy code. So that red line kind of goes up a little bit. And it means that as long as you follow that process, you can be okay with stuff a little bit further towards the full application endpoint. The good thing about this as well is you can end up, if you do this religiously, you can end up with multiple specs. So you get your first one, you get your initial proof of concept or your first version of the application. And then if you want to add a feature to it or change something, you go through that spec kit process and you have another spec. And so you just build this kind of process of specification. Now, there are limitations to this, obviously. Like if you just wanted to go and change some code, now suddenly your spec and your requirements and stuff is a little bit out of sync with your code. So, it's not perfect, but it definitely gives you better results. So that's one. Have a look at that. The other thing, which is a bit more of a technique, is this idea of agents MD. And this is pretty much like a README, but for LLMs. So the idea is, just as you wouldn't, give a one-line description of what you want to a junior developer, you don't give a one-line description of what you want to an LLM. You have a document that outlines how you write your code, how you construct your React components, the structure of the application. These are the things we care about, these are the things we don't. And you can have this one agents MD file in your repo, and it's supported by most of these coding agents at the moment. Or you can build up like these collections of documents as well. So when you are working in the front end, here's the stuff that you care about. When you are doing anything that's visually on the screen, here's what we care about in terms of accessibility. And all of these instructions. And what you'll find is that the agents or the AI, generative AI tools these days tend to do a pretty good job of reading that and implementing things with those guidelines. Now, it's not perfect. Exactly the same way as if you did that same thing with a junior developer. Here is a pile of documentation to read before you implement this thing. You can't guarantee that the code is going to follow all of those guidelines exactly. However, the real power of this is that this can be a living document, and if you start getting incorrect results from the AI, then you can add corrections into the agents MD, and then from that point on, the agents are going to start to follow those rules as well. So you can basically refine the quality as you go, and as the project progresses, you get better and better quality code from your AI agents. We've even done this at GitHub with some of the front-end stuff. The GitHub repo, by the way, is gigantic. It used to be this gigantic monolith, mainly written in Ruby, and we've split it up a little bit. But because there are some pages that are written in like really old versions of Vue, some that are written in React, and so on, what we want to do is we want to kind of migrate the older ones to the new ones. But that's not a find replace kind of job. It's a here is the way we want to structure them and go from whichever system was there before to this new one. So what they've created is this series of instructions basically for LLMs, for Copilot, to first do this, look at these things, make sure that's okay, then move to this step and do that. And it's got to the point now where a lot of the time, like a vast majority of the time, you can say, create this or update this page to the newest framework and just point at a page, and it will run through that stepwise thing, doing the right thing, following the guidelines and the standards that we care about, and produce a page that works, because we also have tests running and things like that. And we don't actually need human input because all of the human input is encoded in these instruction documents. So for long-running projects, this is amazing. It's also really good for greenfields projects in established teams as well. So since April last year, I think, you've been able to set these custom instructions at an org level in GitHub as well. So whenever anybody creates a repository and does some code, these are the instructions that must be followed. And this can be really good for setting those standards for organizations, for the entire organization, whether or not somebody's using a coding tool or not. So this kind of technique of giving instructions to your virtual developers, essentially, is becoming more and more common. One final thing that I want to give you as well is some of the other ways that people have used AI tooling as well to kind of improve the quality of code and improve that whole lifecycle as well. This was a really recent, January 17th, really recent experiment run by David Fowler, who's a distinguished engineer, I think, at Microsoft. Really smart guy. I said I wasn't going to talk about Ralph, so I'm not. But he was basically doing an agent loop which would look through all of the bug reports in, I think this is in the Aspire code base as well. So look through all the bug reports and find the ones that didn't have any repro steps, and then it would create a sandbox and then just hit it again and again and try to create a reliable reproduction of the bug that was described in the bug report. And it's been relatively successful. You should be able to find this relatively easily, but he's got this available so you can have a look at what he did. But what it's meant is this gigantic backlog of bugs that had no reproduction steps now have repro steps, because he's just got an AI to run through and try to hit it and say, okay, this is how you get that problem. That is incredibly useful for teams, right? Burning down that backlog of bugs, using AI to make it a lot easier for human developers to do the work is really, really critical. Or it can be really critical for getting some motion on your applications. All right. I've talked a lot. There is a lot more going on. Oh, by the way, sorry, there's a session on Friday from Yishai Beery on AI code reviews, if you want to know some of the techniques for doing that as well. And apologies for any of the speakers there if I've missed your talk in reference to one of these. I am going to be out at the Microsoft booth after this as well if you want to have a chat about any of this. But I want to kind of summarize what we've talked about now. I started super positively by saying none of you know how your code works. But hopefully you've seen that this AI tooling has the potential to create more probably working software that's really risky. However, there are ways that we can use these tools to make our lives much easier and to trust that code a lot more. I really want the people in this room to think a bit about the impact of failure when AI tools get it wrong, because that's what's most important, right? Because developing software is exercise in trust. We are dependent on so many other people in this industry to get the right code. And if we are just going to ignore all of that trust that we've developed and throw stuff at an LLM and then take whatever it gives us and throw it in production, it feels like we are not being responsible members of the software development community, right? We need to trust everything that's underneath us. Our users and the people using our software should be able to trust that the code that we've written, we've done it with the best of intentions, whether we have written it by hand or whether we've got our AI tools to do it as well. So this idea of, well, it probably works, isn't good enough, right? It's never been good enough, and it shouldn't be good enough now just by throwing stuff at an LLM and assuming, well, it looks like it works, it probably works. However, that's a bit of a case by case. So it probably isn't good enough. If you're writing some code for a Keynote and you're just clicking around some known things, it's probably fine, actually. And if you're writing some code for your friends to share a bit of money when you go on holidays, probably is good enough, actually. But for the most part, if we want this rigor around our software engineering, you need to think a little bit about the quality of the code that you're getting out before you ship it to production. So thank you, everyone. I hope you have a great NDC London, and I'll have a chat to you a bit later.